Secondary rainbow. A secondary rainbow is formed when the incident light undergoes two internal reflections in a spherical drop of water as shown in figure. So first reflection at point B and then C at point D. So it enters at point A, first reflection at point B, second reflection at point C, and point D it refracts. Okay, in terms of the incident angle theta sub A at point A and the refractive index n of the drop, what is the angular deflection of the ray? That is, what is the angle between the ray before it enters the drop and after it exits? So the angle between these two. Okay, so let's take a look at this situation. From the previous problem, we already know that the angular deflection at point A is delta A is equal to the angle of incidence at point A minus the angle of refraction at point A. So if we go back to the previous problem, we can see that here the angle of incidence at point A minus the angle of refraction at point A is the angular deviation at point A. Now we go to point B. This time, the angular deviation at point B is equal to pi minus twice the angle of refraction at point A. So let's take a look at that result. So it is pi minus theta AB and theta RB, but these two are the same, and that is equal to the angle of refraction at point A, because remember that this is an isosceles triangle. Okay, so we have that result from the previous problem. Now if we go to the next point, point C, similarly we will have pi minus twice theta BA, so it's going to be the same situation. So let's see here. If this goes to another point and it reflects, then we will have the same situation because these two angles are the same here. So we will have the law of reflection, twice that angle, minus pi will be the angular deflection at that point. So it's going to be the same situation. So therefore, we have the same answer at point C. And at point D, when it comes out at point D, the angular deflection is the angle of incidence at point A minus the angle of refraction at point A. So if we go to the previous problem, we see that this is the deviation and it is the angle of refraction at that point minus the angle of incidence. So if we look at the situation at this point, because all of these angles are the same, that means we're looking at the angle of refraction at this point minus the angle of refraction at point A, but we have shown that these two angles are the same, so it's basically the angle of incidence at point A minus the angle of refraction at point A. Okay, so if we add these, because we know all of these answers from the previous problem, we can find the total angular deflection, delta. It is twice the angle of incidence at point A, 2 theta AA, minus 6 times the angle of refraction at point A, plus 2 pi. And we also have 1 times sine theta AA at point A, Snell's law, is equal to n times sine theta refraction at point A. So for angle of refraction, we can also write arc sine theta A divided by n. So sine angle of incidence at point A divided by n. With that, we can get the total angular deflection, delta, is equal to twice the angle of incidence at point A minus 6 times sine inverse arc sine of the angle of incidence sine theta A at point A divided by n plus 2 pi. So this answers part A. Okay, now part B. What is the incident angle theta 2 for which the derivative of the deflection with respect to the incident angle theta AA is 0? So we will take this and take a derivative to get the condition for rainbow formation. So derivative of the deflection d delta with respect to the angle of incidence at point A evaluated at the critical value theta 2 is equal to 0. So this derivative, if we look at our result here, the first term will be derivative with respect to theta A. It will give us 2. So this is 2 minus 6 times the derivative of inside 1 over n, and sine will turn into a cosine. So 6 times, so it's going to be 6 over n cosine of theta 2. Derivative of arc sine is 1 over square root 1 minus u square. So it is 1 over 1 minus sine square theta 2 over n square inside the square root. This must be, the other term is 2 pi, so the derivative is 0. So this is going to be 0 when it is evaluated at theta 2. So this gives us, if I isolate cosine theta 2 on the left side here, cosine theta 2 is equal to, now 2 goes to the right hand side, multiplied by n divided by 6, we obtain n over 3, index of refraction over 3. Then we have multiplied by square root of 1 minus sine square theta 2 over n square. Sine square theta 2 over n square, square root. Okay, now we have to take the square of both sides to solve for theta 2. So cosine square theta 2 is equal to n squared over 9. And then we have 1 minus sine square theta 2 divided by n square. And this is, if I take n square inside the parentheses, this is going to be 1 over 9 n squared minus sine squared theta 2, which is 1 over 9. Now I'm going to write sine square in terms of cosine square. N square minus 1 plus cosine square theta 2. So this is n square minus parentheses 1 minus cosine square, which is sine square. So for sine square, I'm substituting 1 minus cosine square. So I obtain 1 over 9 n square minus 1 and 1 over 9 cosine square theta 2. On the left side, I have cosine square theta 2. So I subtract from cosine square 1 over 9 cosine square. I obtain 8 over 9 cosine square theta 2 is equal to 1 over 9 n square minus 1. Or I can write this as, because 1 over 9s will cancel, I can write this as cosine square theta 2 is equal to 1 over 8 n square minus 1. Or I can say that theta 2 is equal to arc cosine square root of n square minus 1 over 8. So this is our final answer for this critical angle theta 2 that we were supposed to find in part B. The incident angle for which the derivative with respect to the incident angle theta A is 0. Now part C, use the results of parts A and B to find theta 2 and delta, the deflection for violet and red light. Do your results agree with the ones shown in figure? When you view a secondary rainbow, is red or violet higher above the horizon? Explain. Now we have the index of refraction for violet, and violet is equal to 1.342. The corresponding angle of incidence, theta 2, the critical angle of incidence, is arc cosine 1.342 squared minus 1 divided by 8 square root. And this gives us an angle of 71.55 degrees for the critical angle of incidence. And if I do the same exercise for red, for which the index of refraction is 1.33, the corresponding critical angle of incidence is theta 2 arc cosine 1.33 square minus 1 divided by 8. This is inside the square root. And that's going to give 71.94 degrees. Okay. Now with that, I can calculate the deflection for violet and red using this formula that I have obtained in part A. So let's do that calculation. The deflection delta for violet is equal to twice the angle of incidence, 2 times 71.55 degrees, minus 6 times sine inverse arc sine of the incidence angle, sine of 71.55 degrees, divided by the index of refraction, 1.3342 for violet, plus 2 pi, which is 360 degrees. So this gives us a total angular deflection of 233.2 degrees, which means the angle above the horizon for violet, theta violet, is 233.2 minus 180 degrees, which is 53.2 degrees. So that is the angle. If we have calculated the angular deflection for violet, so if I subtract from this pi, I will obtain the angle above the horizon. So that's what I have done here. And if I do the same calculation for red, the angular deflection for red is equal to 2 times 71.94 degrees minus 6 arc sine of 71.94 divided by 1.33 index of refraction for red, plus 360 degrees. This gives me an angular deflection of 230.1 degrees. The corresponding angle above the horizon for red is 230.1 minus 180, which is 50.1 degrees. So we can see that if we compare these two, the violet, the answer for violet is greater than the answer for red. So our conclusion is that theta violet is greater than theta red. Violet appears above the horizon. So that's the answer to part C of the problem. Now, I have used the results of the previous problem to calculate the total angular deflection. This is the direction of the incoming light. This is the direction of the outgoing light. So this is my total angular deflection. At point A, I have theta AA minus theta BA. At point B, I have pi minus 2 theta BA. At point C, I have pi minus 2 theta BA. And these basically come from the fact that the situation at point B and if I had another reflection at point C would be identical because these angles are the same. So you would have the same situation for the angular deflection at a point C. And at point D, I have the angle of incidence at point A minus the angle of refraction at point A. Exactly the same result I have obtained in the previous problem. So this gives me my total angular deflection, and once I write Snell's law at point A, so this is Snell's law of refraction, I can write the angle of refraction in terms of the angle of incidence, and I get the total angular deflection. Now, if I take the derivative of the total angular deflection with respect to the angle of incidence and set it equal to 0 at a critical angle theta 2, I find that theta 2 must be arc cosine square root of n squared minus 1 over 8. And if I use the index of refraction for violet and red and evaluate that critical angle, I find the angle of incidence to be 71.55 and 71.94, which I can substitute into this result to get the total angular deflection for violet and red. So for violet, I obtain total angular deflection 233.2. If I subtract 180 from this, I get the angular deflection above the horizon. So that gives me 53.2 for violet, 50.1 for red. So I see that the violet appears above the horizon because the angle for violet is greater. So if I compare that to the result of the previous problem, I had red appearing above the violet. So you can see that the order of the colors that we see above the horizon changes depending on whether it's a primary rainbow or a secondary rainbow.